Okay guys, let's do part B here and finish out 15.1. Let's check if this vector is this vector field is conservative. So again, I need to check that the y partial of my m function and the x partial of my n function, if they're the same. If they are, it's conservative. So let's distribute here. This is 2xy e to the x squared y I plus x squared e to the x squared y j. So check the y-th partial here. So this is 2x times what will be product rule. So that'll be e to the x squared y times, or plus, y times derivative of this thing. So e to the x squared y times x squared. So in total, this is 2x e to the x squared y plus 2x cubed y e to the x squared y. Now let's check the x partial here. It is, we've got x squared times the xth partial, which is e to the x squared y times 2xy, plus the derivative of this thing, 2x times e to the x squared y. So in total, this thing is 2x cubed y e to the x squared y plus 2x e to the x squared y. Now it turns out these are both equal to each other, so this thing is conservative. Okay, so an extension of conservative is to be irrotational. So to figure out what irrotational means, we need to define the curl of a vector field. The curl of a function in 3 dimensions is the cross product of a gradient and the function f of x, y, z. It's equal to dp dy minus dn dzi, dp dx minus dm dzj, plus dn dx minus dm dyk. And if the curl is 0, then f is said to be irrotational. So the above can be cleverly set up into a matrix. It's not really a matrix multiplication so much as it's matrix vector derivation. This picture here, just by looking at these, is the matrix ijk and the x, y, and z partial derivatives, and then it should be m, n, and p. It's just m is cut off here. Okay, so if you're asked the question if something's irrotational, it's basically like being asked if it's conservative on steroids, because not only do the partials for x and y need to match up, the combo partials for x and y and z also have to match up. So let's look at these partials. We have our f of x partial, 2xy. Our fy partial is x squared plus z squared. And our f of z partial is 2yz. So I need to show that f of xz is equal to f of zx. So the zth partial derivative here is 0. What's my f of zx? My x partial from this one is 0. Those two are even, so that's the first check. If one of them is not equal, it's automatically not irrotational. You can stop. Let's check fyx. The derivative with respect to x here is 2x. What about f of xy? Derivative of this thing with respect to y, also 2x. Now the one we're missing is f of yz and f of zy. So f of yz is 2z. F of zy, derivative of this with respect to y, also 2z. Now, because they're all 0, what that means here is, or they're all equal to each other, that means when I subtract them up here, they're all going to be 0, which means the whole thing is 0, and when the curl is all 0, it's irrotational. So yes, this is irrotational. So you've seen that a curl of a vector field is itself a vector field. Another important function defined of a vector field is called the divergence, which is a scalar function. This is just a reminder to test for conservative vector field in space and its relationship to irrotational. So let's define the divergence of a vector field, and that will be, do one problem, and that'll be all for 15.1. Okay, the divergence of a vector field. The divergence of f of xy equals mi plus nj is the gradient, the dot product of the gradient time and f of xy. It's really not a dot product so much as it's a dot derivative. Namely, we're taking the derivative of the x partial of the first function, normally the x function, partial to x, and the second one partial to y. Similarly, we would do the same thing in 3 dimensions. It's not really dot products so much as dot derivatives. We're kind of entering a new phase where it's not so much products. It's just an easy way to understand what's happening. So when it says find the divergence of the vector field at a point, we need to take our partials with respect to x, y, and z in the order that they're placed. So the partial with respect to x here is 3x squared y squared z. Partial with respect to y is 0, because there's no y, and the partial with respect to z is also 0. Now I add them all up, so it's 3x squared y squared z plus 0, which is really just 3x squared y squared z. And I want to evaluate it at 2, 1, negative 1. So that's 3 times 2 squared times 1 squared times negative 1, which should be negative 12. So the divergence of the function at the point 2, 1, negative 1 is negative 12. So one theorem here at the end, for the end of 15.1. Divergence and curl. If f is a vector value function, is a vector field, and m, n, and p have continuous second partial derivatives, then the divergence of the curl of f is 0. That's just a little piece of information there. Sometimes you can use that to check the curl. And that's all for 15.1.